Assalamualaikum, good afternoon. Can you hear me?
Yes, Doctor.
All right. Okay. We refer to the slide number 61. Okay. Everybody refer to slide number 61, rule number 7, which is the rule locus crossing at the imaginary axis. Okay, as shown here. This is your imaginary axis. This is your real axis. And the rule locus is on the blue line. Okay. But before that, we try to read from the root locus plot the open loop transfer function. Okay. So start with K, the gain, and zeros. Is there any zeros here? Open loop zeros? No. So, oh, sorry, we have there -3 there. So is a S plus 3 divided by Alia. Alia, mute your microphone, please. Thank you. And then we have 1, 2, 3, 4. 4 open loop poles start from 0, -1, -2, -4. So it will be S plus 1, S plus 2, and S plus 4. Okay. So 4 open loop poles and 1 open loop zeros. Okay, with the K varying around on the root locus plot. So our concern is the crossing intersections, or we call it as intersections between the root locus and j omega imaginary axis. Okay, so that is what our concern for rule number 7. And in order to do that, we have to what do you call that? Use a tools. We call it as a Ruth-Lewis. Okay, so Ruth-Lewis is the tools to calculate the intersections. Okay, so the j omega axis crossing is a point on the root locus that separate the stable, unstable operations. As I told you previously, okay, in the for the root locus plot, okay, okay, this one is a right half plane. This one is the left half plane. And this part is the imaginary axis. Okay, so we have three area now. Okay, which is we call it as stable, unstable, and this part is critical. Okay, so the location of the poles plays an important role. Okay, uh, to decide whether the system is stable or non-stable or critical. If all the poles located on the left half plane, so no issue. Okay, no issue. It's stable. But if there is a pole, even single pole on the right half plane, so it will be unstable, definitely. An unstable system is not good, it's not safe, and can cause accident uh, towards the system and the human. Okay, so therefore another one is critical. Okay, so critical is on the top of imaginary axis. So critical is 50-50. It can go to stable, it can go to unstable, but it's critical. That's why it is the pulse is on the imaginary axis. This is the concept that you must understand first. Okay. So therefore, we use the Ruiz criterion, okay, in order to do the to find the intersections between root locus and imaginary axis. If you still don't remember, or maybe last semester we studied the Ruiz table concept, I revisit again, okay, recall again. We have input R, we have output C, and we have the what do you call this the characteristic equations. Okay, characteristic equation. And this characteristic equation consists of coefficients of A4, A3, A2, A1, and A0. And this one will coefficient will enter to the Roth-Lewis table as shown in the slide number 62, where we have a A4, A3, A2, A1, A0, and 0. After that, we fill up all the empty space of the Roth-Lewis table using the formula that shown in this table. Okay, bear in mind that this one is what? What is the symbol of that? Left and right. Or if and absent. Amira Suraya, what is the symbol of this left and right?
I forgot.
You forgot. I told you. Nurul Najiha? Tak datang. Chen? Tak datang eh. So is a determinant. Okay.
Magnitude.
Huh? Salah. Determinant. Okay. So determinant meaning that it will be minus A4, A1 minus A2, A3. So that one is A4, A2, A3, and A1 is a matrix. Okay. So that left and right straight line, we call it as a determinant. Please jot down. And then it's continue for B1, B2, C1, D1, and so on. Okay. And for Roth-Lewis criterion, we have a special case, two special case. The first case is when 0 in the first column. Okay, 0 in the first column. Column meaning this one, column. And the second one is the entire row is 0. Entire row meaning is the horizontal. Okay, vertical and horizontal. So for 0 in the first column, for example, we have this closed loop transfer function with given characteristic equation. You plug in, and then the number of 0 you replace with epsilon. Okay, so epsilon is a simple number, positive or negative number that can be used in the first column to see the polarity, whether it is positive or negative. So in this case, we observe the sign change, positive, 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 negative, meaning that there is one sign change. And the second one, negative to positive, second sign change. Okay, so second sign change, meaning that we have two poles on the right hand side. And then a row of zeros is shown here. Okay, when we have this row of zeros at S cubic, what we will do is we find the auxiliary polynomial. Okay, PS. And then we take from S power of 4, then we differentiate. Okay, 4S cubic, 12S plus 0, and then we insert back inside the row of zeros. Okay, so you will refer again to the module for your notes last semester. Right, so example 6, guys, is we are given open loop transfer function as shown here, this one. So find the frequency and gain K for which the root locus cross the imaginary axis, and give the range of K when the system is stable. So from here, you can see that we have a single open loop zeros. Okay. Nasrun? Nasrun,
Yes, saya.
what is the value of open loop zeros?
Negative 3.
23, thank you. And how many open loop poles?
4.
4. And what is the values?
0, negative 1, negative 2, dengan negative 4.
54. And then we have a unity feedback, which H is equal to 1, okay? Right, so we find the closed loop transfer function from open loop to closed loop, okay? So let's say this one is the GS. So to find TS is you take the open loop, insert inside this formula, GS over 1 plus GS, so that you get closed loop. This is the closed loop transfer function, guys. Okay, and the bottom denominator of the TS or closed loop transfer function, we call it as, what is the name of this equation? Muhidul?
Yes, sir.
What is the name of this denominator equation?
Uh, I forgot actually. I don't remember.
You always forgot, huh? What do you eat, huh? Muhidul? Chawal, huh? You eat chawal? Huh?
Yeah.
Too much chawal. Juan, Howley?
Yes, doctor.
What is the name of this equation?
Characteristic equation?
Again?
Characteristic equation.
Yes, characteristic equation. Muhidul, take note.
Yes, sir.
Right? So from the characteristic equation, we insert the coefficient for S power of 4 is 1, 7, 14, 8 plus K, 3K. And this one, 0. And then continue the fill up. Okay, so I don't want to show this one. You already can refer to this formula because this is the one that you learned already in the last semester. Okay, you just use this formula. Okay, and then you will get this polynomial on S square, S power of 1 and S power of 0. So the theory said for stability, okay, first column of Roth-Lewis table as greater than 0. Okay, so this is first column. You can see that this is the first column. And 1 is greater than 1. Okay. 7 greater than 1. Okay. So we have a K in these three equation. Okay, which is 90 minus K. Okay, 90 minus K greater than 0. Minus K greater than minus 90, K less than 90. Okay. Okay, so this is equation number 1. Equation number 2 is this one, minus K square, 65K, plus 720 over 90 minus K greater than 0. Simplified. Simplified. And then find the roots. Okay, please use your calculator. Anik. Anik. Muhammad Anik.
Yes, Doctor.
Use your calculator, please. Find the roots.
Root number 1, 9.65. And root number 2, negative 74.65.
Apa yang Asrun, off your mic, please. You already off your mic. Siapa yang bising? Okay, so that is the value. Okay. And if we use MATLAB, we just write there, create the K vector. Okay. Then find the roots. Okay. Then we'll give the same answer. Right. So therefore, 9.64, K is equal to 9.64. That's why the range is 0, K, 9.65. Okay. If K is equal to 4, system stable. If K is equal to 9, system stable. If K is equal to 10, system stable or not stable? My question goes to Lee Jiajing.
Yes, not stable, Doctor.
Not stable. If K is equal to 9.65, Lee Jiajing.
Not stable also, Doctor.
Salah tu. Chong Ka Jun. When K is equal to 9.65, is it stable or unstable?
Marginally stable.
Is critical or marginal. Please take note. Okay. K is equal to 9.65, critical or marginal. Okay, guys. So why I mentioned that? Because if we plot here, okay, the 0, -1, -2, -3, -4 is here. Okay. This is where the K is equal to 9.65, where it is critical stable. Critical. Okay. So critical stable and critical dam is two different things. Most of the students say it's the same. Actually, it's not the same. Please take note, guys. Okay. So when the root locus at the imaginary axis, the zeta is 0. When the root locus at the real axis, the zeta is equal to 1. And this part of the quadrant, the green quadrant, is between 0 and 1. The most area that we want the system in our design. Okay. But over here, on the right-hand side, the zeta is already less than 0, negative. Okay. Negative unstable lah. So please make sure that you don't assume critical stable and critical damp. It's not the same thing. Okay. So most students said that zeta 1 is critical damp or critical stable. Actually, it's wrong. Okay. So please take note about that. So when K is equal to 9.65, which is over here, the system is critical or marginal. So we use this K. Okay, we insert inside the growth table equation, which is here at S square. Use S square rho equation. So you will get 90 minus K plus 21K, okay, S square. So you replace K inside here, 9.65, and then you get 80.35 S square plus 202, okay. Square 202.7. Simplify. Gabriel, help me. Gabriel. Hello, Gabriel. Help me. Tak datang. Tak datang ni. Izha, help me. 202.7 divided by 80.35.
2.522.
2.52.
52.
Then square root. Berapa?
1.588.
Huh?
1.588.
588. Okay. So that is the value of the point at the imaginary axis. Okay. So the system is stable for K0, K 9.65. And what is the value of the oscillation frequency? So when the response, the time response for critical stable is oscillations. Okay, guys, is the oscillations. And this oscillation have a frequency value. Okay, we call it as the oscillation frequency, which is omega. So J omega equal to J 1.588. So therefore the oscillation frequency is radian per second. Okay, guys, understand? Hello?
Yes, Professor.
All right. Right. So I hope you understand the three areas, which is the stable on the right half plane. Okay. Sorry, left half plane. Unstable, right half plane, and critical at the top is on the imaginary axis. So we simulate using computer. Okay, so the gain is 9.65, correct? Okay, the damping is damping 0, correct? The one that we calculate, berapa tadi? 1.59. This one is 9.65. Okay, so by computer is more accurate because it's using the interpolation and so on, and then the damping 0. Okay, and the frequency is 1.59 radian per second. So same as what we calculate just now in the whiteboard. Okay, this one. Any question, guys? Any question to ask? Anis, Farisha, ada soalan?
Tak ada, Prof.
Clear,
Okay, Prof.
clear. Right, so we move to the rule number 8. We call it as angle of departure and angle of arrival. So theta arrival and theta departure. Okay. So angle of departure is related to the complex conjugate pole, while theta of arrival is related to complex conjugate zeros. Okay. So use for the open loop poles and zeros, as I mentioned in the blue line there. And then the rule locus depart from the complex open loop poles and arrive at the complex open loop zeros. Okay. And the angles can be found by using the angle property for theta arrival is the summation of angle all poles to B minus the angle of poles 0 to B plus 180 degrees. And theta D is angle of all zeros to A minus to the summation of angle of all poles to A 180 degrees. The A and B point is refer to this diagram. Okay, this diagram. A and B. Okay. So we can see that for the angle of departure is complex conjugate poles, CCP, which is here. And angle of arrival is based on complex conjugate 0, which is here. Okay. And the formula is written there. Theta 1, okay. Theta 2, theta 3. Theta 1, where is theta 1? Theta 1 is here. Is a complex, is a pole. Theta 2 is the zeros. Theta 3, the zeros. Theta 4 is poles. Theta 5, poles. Theta 6, zeros. Equal to 2k plus 1, 180 degrees. And this one also the same, use the same concept as the previous formula. Okay, so equal to 2k plus 1, 180 degrees. Example 7. For the unity feedback system, find the angle of departure from the complex pole and sketch the root locus. Zaim, Ryan. Zaim? Sleeping. Darren?
Yes, doctor.
What is the open loop zeros?
Zeros -2.
What is the open loop poles?
Poles -3.
Mm-hmm.
And then the back one is imaginary. I need calculator.
Do you have calculator?
-1 plus I and -1 negative I.
-1 plus minus J1 lah.
Yeah.
So -1 plus minus J1 is two poles. Yosef, Afi, Yosef, sleeping. Malik,
Yes, doctor.
-1 plus minus J1 is a complex conjugate poles, correct or not?
Correct.
Huh?
Correct. Sahih.
Okay. That's why in this question, off your mic please. Asking for angle of departure. So angle of departure is related to complex conjugate poles. The question didn't ask angle of arrival because there is no complex conjugate zeros. Okay, so be clear about it. Okay, so -2, guys, -2 is here, 0 -2, and then -3 is the poles, and then complex conjugate pole at -1 plus minus J1. Okay, guys? This is the origin, real axis, imaginary axis. Okay. So we have 3 root locus. Okay. 3 root locus because the open loop zeros have open loop poles have 3. Okay. So now we have to calculate the angle of departure. So angle of departure is, we noted here, θ1. θ2 is the the twin brother of θ1, θ2. Okay, so θ3 due to the poles at due to the zeros at -2, and θ4 is due to the poles at -3. So we have to calculate what is the angle of departure for θ1. So we use the formula lah. This one that written in the previous slide. Okay. Then θ1 will be θ3 minus θ2 minus θ4, 180 degrees. Okay. The problem now is how to measure θ3, how to measure θ2, and how to measure θ4. Okay. Chu Yong Jun,
Yes, doctor.
how you measure θ3?
Tan
Using what?
using tan shift
Using tan. You cannot
inverse
using
tan.
tan, ma.
Huh?
Cannot use tan, ma. Tan is a human.
Inverse tan.
Huh?
Tan 1/1
Inverse tangent. 1/1 berapa?
45 degree.
45 positif Okay. theta 3, okay. And then how you measure theta 4? Liu Hongyao.
Yes, doctor.
How you measure theta 4?
Tangent inverse 1/2.
Berapa?
Wait, 26.57.
Share. Ang Jongming.
Yes, doctor.
How you measure theta 2? Ang Jongming. Tak tahu ah. 90 degrees Oh. Okay. So theta 3, 45 degrees. Theta 4, 26.57. Theta 2, 90 degrees. Insert inside. Okay. Then find the theta 1. Okay. So theta 1 will be minus 200, sorry, 108.4. Meaning that this one, you have to plus 360, so you get 108, which is over here lah. So this is 90 degrees, so it a little bit to the left, so it is a 108.4. That is your theta 1. Okay. Right. Rule number 9. Plotting and calibrating the root locus. Okay, all points on the root locus satisfy the magnitude and angle properties. Okay, that is a must. Okay, so that we can confirm that that is the closed loop poles. Okay, so we may want to locate points on the root locus and their gains. Okay, for example, when the root locus cross the line representing 20% overshoot. Okay, so what is the gain over there? So 20% overshoot, usually we refer to a graph that will give you the zeta value. Do you remember the graph? Do you remember the graph or not? Anybody remember that graph? Okay, see your WhatsApp. Okay, you receive my WhatsApp referred graph. Fun? It's fun.
Yes.
Can you give me the value of zeta when overshoot is 20%? Use the second graph. I think it's about 20% is about
0.46.
20% overshoot.
Then the damping ratio is 0.46.
46, confirm, Okay, 0.46. Okay, and zeta is a straight line. Okay, as I told you before, this is the origin. So the nature of zeta is a straight line. So somehow dia macam ni. Okay. Okay. 20% overshoot is zeta 0.46. So this is the zeta line, 0.46. And there is a, what do you call that, angle over there, theta. Okay, so cos theta is equal to 0.46, which is zeta. So therefore, zeta is inverse cos 0.46. Miss Fan, can you silap,
62.61.
sorry. Okay. Huh? Wait, theta is equal to
Inverse cos 0.46 equals to 62.61.
0.46. Theta equal to
62.61.
okay, thank you very much. Okay, which is here, the angle of here. Okay, this angle. All right. So and at that point, you can calculate the gain. Okay, which is 1 over GSHS, or 1 over the magnitude, which is the finite post length or finite post zero. Okay, this is one formula. There is another formula which are using the magnitude formula. Okay, so let us see this one, the example. For a unity feedback system that has the forward transfer function, which is here. Okay, so we have one open loop zeros, which is -2. And we have two open loop poles, which is here. Can you help me to find the roots? Lau Baoliang, help me.
2 plus minus J3.
Huh?
2 plus minus J3.
Minus J3 on the right hand side, confirm, right hand side. So we sketch the root locus and then we find the J omega axis crossing, and then find the gain K at J omega, then find the break in, and then find the angle of departure. Departure due to the complex conjugate pole CCP, i.e. 2 plus minus J3. And then verified using MATLAB. Right, so this is the plot, okay? So plus J3 minus J3 is a complex conjugate pole, but on the right hand side. And then the other one is -2. Where is -2? It is zeros. Okay. Oh, beta. Okay. So the plotting start from here. Poles. Okay. The root locus start from poles, and then what is the name of this point?
A breaking point?
Break.
A break-in point.
Break-in point. Fakihah Sofia, betul ke? This one? Fakihah Sofia? Tak datang. Break-in point, guys. Okay. And then one goes ended at -2 zeros, and the other one ended at infinity. Okay. So now we are going to calculate, okay, the over here, okay, the intersection. Root locus, okay, and J omega axis, okay. And then we want to calculate this one. We want to calculate this one as well. And then we want to calculate the angle theta departure. Okay. Okay, guys. Without any further ado, go to the closed loop transfer function. Okay, closed loop transfer function, where we insert the GS, open loop transfer function, over 1 plus GS. And then we get the characteristic equation, which is equal to 0. Okay. Remember, Then put inside the truth table as shown. Okay. And then simplify. Okay. This one is first column greater than 0. Okay. So we found that K is equal to 4. Okay. K is equal to 4. Range of stability. Insert K inside this equation of S square. Then you will get the S value at 4.58 radian per second, which is this one. J 4.58. Okay. And therefore the oscillation frequency is 4.58 radian per second. Okay. And then from the break-in point, okay, so this is the open loop transfer function. So S plus 2 over S square minus 4S plus 13, differentiation. Okay. If you don't remember, the formula is like this. V du U dV over V square equal to 0. Okay. So you get the quadratic equation simplified, and this one is you find the roots. Okay, guys, you find the roots. We have 3 values, -7 and +3. So which one is related? I don't think it's +3. It should be here, am I right? -7 is the break-in point. So +3 is not related, so we ignore this one. We choose -7. And then for the gain value at the break-in point at -7, okay, is calculated by this formula, which is K L1, L2, L3 is the length. Okay, so this is +2, and the length of here is, guys, is J3, am I right? So this is 3. Okay, and then the length of this is 7 is 9. So L1 is the square root of 9 square plus 2 square, which is equal to, guys, 9.48. 9.48. Similar to L3, similar to L1, and L2 is the length is, this one is -2, so the length is 5. Okay, so that's why divide by 5. And K is equal to 18. Okay. Or if you don't want to use this, you can use the formula that I teach you, which is S square minus 4S plus 13. S square minus 4S plus 13, plus 13 divided by S plus 2. Then replace S with -7. You insert s minus 7 inside and find the magnitude. So you will get the value of k is equal to 18 as well. Okay, so we have both formula, both ways to do it. And for the angle of departure, as shown here, use the formula straight away, use the formula, the angle of theta departure. And then you will get the value of theta is minus 233.1. Okay, so minus 233.1, which is over here. Okay, the angle of departure. All right. And then we completed our calculations and verified using the MATLAB. Okay. So we get the same answer as in the manual solution. Okay. Okay, this one we stop here. Nurul Najiha. Nurul Najiha.
Ya, dokter.
Slide 83 stop.
Oke.
Wakaf. Slide 80, slide 83. So now is for the attendance. Do you have any question, guys? Any question? Section 7 first. Section 7, 33 student.
Sir,
Yeah.
is there any QR code for attendance today?
Yeah, I'm sharing now. This system very slow. You copy image. Section 7A. Okay, section 7 please scan. Section 8 do not scan. So you nanti ada problem nanti during registration. Okay, attendance. Section 7 first. Section 8 keep quiet. Section 7 scan first. Guys.
Sorry, doctor, the screen is not shared yet.
Allah. Akhi, section what?
Section,
Akhi. What section?
section 7.
7. Allah. Ya. Share my 7.
Right, doctor.
Can?
Yes, doctor.
Okay. So we go for section 8. Guys, please be patient. Section 8. Section 8. Okay, section 8. I share now. Section 8 can scan now.
Prof, can go back to slide 80.
At 80. Question.
Just now you write method 2 to get the
So,
equation.
wait, ah. This one, where?
Yeah, thank you, Prof.
Huh? Dah.
Yeah,
Uh,
done.
I will
Thank you, Prof.
share. I will share in the YouTube. Don't worry.
Okay.
View from the YouTube. Okay, guys. Any question? Attendance dah ambil. Muhidul. Attendance.
Yeah, done, sir.
Okay ah.
Okay, okay.
Yeah.
Thank you, Doctor.
I would like to take this opportunity to wish a selamat Hari Raya Aidilfitri. Okay, to the Muslim brothers and sisters, Arab brothers, Eid Mubarak, Minal Aidil wal Faizin, Abdul Malik, and all the Arab brothers. Okay, thank you. And for the non-Muslim, happy holidays. And we're going to see face to face, inshallah, on the 8th of April. Okay. So wait for my instructions later. Happy holiday, guys.
Selamat Hari Raya, Doctor.
Selamat Hari Raya semua.
Sir, do we have class on Tuesday and Thursday?
Next week, no class. Next week, Monday, public holiday, Hari Raya, number 1. Tuesday, Hari Raya, number 2, public holiday. Wednesday, Thursday, Friday, I give off free. Okay.
Okay.
Okay,
Thank you,
guys.
sir.
Okay, Nurul Alia, okay. Okay, thank you very much. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doctor.